Okay, this video goes out to all those hardworking first semester general chem students who are finding themselves in the thermochemistry chapter in their course. And specifically, what we're going to do is work a problem that comes from Hess's law, and will illustrate the various Hess's law rules for dealing with the change in energy at constant external pressure when we have a series of chemical equations that are going to be added or summed together. The rules basically are the following. If you reverse a chemical equation for which there is delta H, for which there is a delta H value, you utilize the magnitude of that value, but you change the sign. So in other words, when you reverse a reaction, delta H, the magnitude of delta H stays the same, but you flip the sign. If we multiply through by a coefficient, you must then take the coefficient and multiply through the delta H. When we have summed together all of the equations and successfully found the equation that we're interested in, then we must sum the delta H's to find the change in energy for that particular reaction. Right now, in this example, the goal is to find the delta H for this chemical reaction here, given the following they call it thermochemical data. So we've got three chemical equations, balanced chemical equations, for which we have a delta H given, correlating to each of those reactions. Now, just as an aside, you can see that the delta H for each of these reactions that we're going to be summing together is a negative number. This means that all three of these reactions in the direction that they're written at the moment are exothermic and releasing energy as they go to completion. Now, our target equation I've circled in red, and you can see that the main thing is there's only one product, and it's C5H12. So when you inspect these three equations, you can see that right out of the gate, we're going to need to reverse this top reaction. All right, we're going to rewrite that going in the other direction. So I'm going to go ahead and pull that down and take care of that maneuver. So we're going to go 5 CO2s plus 6 H2Os. And I should mention that in this business with the thermochemistry, you need to pay attention to the physical states of the components. I see I dropped that out of this one. Now, with that said, as we go through this process of adding the equations, to make life simple, we've already established what these things are here, and so I'm going to, just to be brief, I'm going to leave them out. It makes it just more efficient to write the equation, but you need to pay attention to this initially, because if you have a situation where, like with this water here, you can see it's in the gas form here and it's in the gas form here. The reason you need to pay attention to that is because if there is a switch in phase, that's going to alter the delta H value somewhere in this process, because a phase change requires either the introduction of heat or the removal of heat energy. Alright, so getting back to it, we're going to flip this first equation so that we get the product that we want on the right side of the arrow, on the product side of the arrow. And when we flip it, like I said at the beginning of the video, we need to also change the sign of the delta H, which I'm going to go ahead and do right now. I don't think it's smart to wait to do that until the end of the problem. I think as you go through this, one of the things I do is I continually rewrite steps so that I don't make mistakes, and alter, whatever you've got to do, make the alteration in the delta H plainly so you can see it, so then at the end of this, when you have to add things together, you don't lose track of what you did. All right, now let's take a look at this second reaction, and you see that the carbon is on the correct side, so we don't have to flip this equation. But notice that there's a coefficient of 5 in the final equation, and so we're going to rewrite this, and let's go ahead and we'll multiply this equation through by a 5. And remember, when we do that, we need to also multiply the delta H. So let's take a look at that now. So this is going to be 5 carbons plus 5 O2s, and we will produce 5 CO2s. And the delta H is going to equal a minus 1967.5 kilojoules, and that's after having multiplied 5 through minus 393.5. If you need to pause the video to catch up with me on that, go right ahead. Alright, so I've taken care of the delta H that results by multiplying a 5 through this chemical equation. I mean, basically what we've done is we've run this equation at a magnitude 5 times more than what the delta H was for. So we need to account for now that amount of energy would be released if we, instead of using 1 mole of carbon with 1 mole of oxygen to produce 1 mole of CO2 and minus 393.5 kilojoules of energy, now we're using 5 times that amount, so we're going to get 5 times the energy released. Alright, and then let's take a look at this last equation. Go ahead and change my color again here, so I'm going to go ahead and write it in. We're going to have 2 H2s plus O2 going to 2 H2O. Now, I'm not going to put my delta H in yet because I want to inspect the equations here and start to rationalize what's going to happen when we add these together. Alright, now we see in the final equation that the only thing in the reactant side is the carbon and the hydrogen gas, and the only thing on the product side is the C5H12. So we're going to need to get rid of the oxygens, and we see that in this top equation that there are 8 oxygens. Currently, on the reactant side of this thing, we only have 6. So we're going to have to multiply through this equation by a 3. All right, and that's going to get us to 3 oxygens here, and 5 and 3 is 8. And once we do this, we can take into account the rest of these, but you can see right now that the water is going to do the right thing as well. 3 times 2 on that will give 6 of these to cancel with these waters here. So let's go ahead and take care of this. It's going to be 3 times the delta H for this, which is minus 483.5 kilojoules, and that total is going to be minus 1450.5 kilojoules. All right, now I'm going to go ahead and rewrite all this one more time so that it's abundantly clear what we have to cancel. So we're going to have 5 CO2 plus 6 H2O on the top reaction going to C5H12 plus 8 O2s. And in the second reaction, one other piece of advice, I try to put all my arrows literally one over the top. It makes it easier to avoid mistakes when you're doing this, because it's easy if the arrows are not aligned to not recognize visually when something is on the same side of the arrow when you're comparing this thing vertically up and down. Alright, and then let's see. This last one's going to be 6 H2s plus 3 O2s. And then that's going to make 6 H2Os. So now we're ready to sum this thing together. And let's see my delta H's. I'm just going to go ahead quickly and put the numbers in. So it's going to be 324.8 kilojoules for that one, minus 1967.5 kilojoules for this one, and minus 1450.5 kilojoules for that one. All right, now let's see how we do on the canceling here. So we got these 5 CO2s cancel with these 5 CO2s. This 8 O2 here cancels with these 8 oxygens. Do it that way. All right, and then these 6 H2Os cancel with these 6 H2Os right here. And now when we sum this together, we can see that we're going to get the correct equation. It will be 5 carbons plus 6 hydrogens to produce C5H12, which happens to be pentane, right, in its liquid form. And then we need to finalize this, and you can see what's going to happen. So we've coupled 3 chemical reactions. I want to use that word coupling because if you're taking biology at this time, at the same time you're doing your thermochemistry, this will be perhaps the first time where you can actually see coupling in action. And when your biology teacher's talking about coupling reactions on the molecular level in cells, this is exactly what we're talking about now. They're utilizing Hess's law to do that. So we get this equation out after we sum these 3 chemical equations. The total energy budget now is going to sum, when we add this up, to a minus 173.2 kilojoules of energy. All right. Now, very quickly, I just want to confirm on my calculator that I didn't make an error with that. So it's 3244.8 minus 1967.5 minus 1450.5. Minus 173.2. So in finishing the video, we can see that we can find the delta H for an unknown chemical reaction if we have chemical equations that we can couple for which the delta H is known. So if we were to utilize these 3 chemical reactions in some sort of productive way, we could generate the product that we have down here, and the delta H that we summed lets us know what that energy budget is going to be, and in particular this reaction would be exothermic. And one last thing, if we were to write an energy diagram for this, alright, this is what it would look like, the back of the napkin thing. So we have reactants going to products, and the reactant platform should be up here above the product platform, where the delta H for this thing is going to be negative. Negative a minus 173. All right, which means that the products of this reaction are at a lower potential energy than the reactants were. And with that, I'm going to go ahead and close the video.